Hello everyone. In this video, let's understand how the Peterson solution is gonna work for the critical section problem. Firstly, let's understand what is the critical section problem. For suppose, consider a system consisting of n processes P0 to Pn. Each process has a segment of code called a critical section, in which the process may be changing common variables, updating a table, writing a file, and so on. The important feature of the system is that when one process is executing in its critical section, no other process is to be allowed to execute in its critical section. So the thing is, no two processes should be executing in their critical sections at the same time. Now, the critical section problem is to design a protocol that the process can use to cooperate. Basically, each process must request permission to enter its critical section. The section of code implementing this request is the entry section. The critical section may be followed by an exit section. The remaining code is the remainder section. You can see this here in the slide. And in the slide number 4, you can see the general structure of a typical process PI. Here, the entry section and exit section are enclosed in red boxes to highlight these important segments of code. Coming to the finding solution of a critical section problem, we must follow 3 conditions. The first condition is mutual exclusion, and the second condition is progress, and the third condition is bounded waiting. Firstly, let's know about mutual exclusion. Here, if a process PI is executing in its critical section, then no other processes can be executing in their critical sections. So this is very basic. And then coming to the progress, it means if no process is executing in its critical section and some other process wishes to enter the critical sections, then only those processes that are not executing in their remainder sections can participate in designing which will enter its critical section next, and this selection cannot be postponed indefinitely. So again, coming to the bounded waiting, it means there exists a bound, or we can say a limit, on the number of times that the other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that the request is granted. And assume that each process executes at a non-zero speed and no assumption concerning relative speed of the n processes. Now let's know about the Peterson solution. It is a software-based solution to the critical section problem. We present the Peterson solution because it provides a good algorithm description of solving the critical section problem and illustrates some of the complexities involved in designing software that addresses the requirements of mutual exclusion, progress, and bounded waiting. However, Peterson's solution is restricted to 2 processes that alternate execution between their critical sections and remaining sections. Now, the important thing is the Peterson solution requires the 2 processes to share 2 data items. The first data item is a variable turn of integer data type, and the other data item that needs to be shared is a flag array of Boolean data type. Here, the variable turn indicates whose turn it is to enter its critical section. That is, if turn equals I, then process PI is allowed to execute in its critical section. The flag array is used to indicate if a process is ready to enter its critical section or not. For example, let's assume flag of I is true. This value indicates that the process PI is ready to enter its critical section. If the process PI wants to enter the critical section, at first it sets flag of I to be true, and then it sets turn to the value j, thereby asserting that if the other process wishes to enter the critical section, it can do so. If both processes try to enter at the same time, turn will be set to both I and j at roughly the same time. But we know that only one of the values can be assigned to the turn variable, and the other, which cannot be assigned, will occur but will be overwritten immediately. Now here in the slide 7, you can see the structure of process Pi in Peterson solution, which is different to the structure of general process. I mean general structure of a typical process Pi. To prove or to know that the Peterson solution is correct, we need to show that the mutual exclusion is preserved, the progress requirement is satisfied, and the bounded waiting requirement is met. If these conditions are satisfied, then only we can say that the Peterson solution is valid for the critical section problem. And in the slide 8, you can see the two processes executing concurrently. So, let's see how the property 1 is proved, that is, preserving the mutual exclusion. We note that each Pi enters its critical section only if either flag of j is false or turn equals I. Also note that if both processes can be executing in their critical sections at the same time, then flag of 0 equal to flag of 1 equal to true. These two observations imply that P0 and P1 could not have successfully executed their while statements at about the same time, since the value of turn can be either 0 or 1 but cannot be both. Hence, one of the processes, for example, let's say Pj, must have successfully executed the while statement, whereas Pi had to execute at least one additional statement. Let's suppose turn is equal to j. This is the additional statement. However, at that time flag of j equals true and turn equals j, and this condition will persist as long as Pj is in its critical section. As a result, we can say that mutual exclusion is preserved because no two processes are executing in the critical sections at the same time. Now let's prove the other two properties, that is, the progress requirement should be satisfied and the bounded waiting requirement should be met. To prove these properties, we note that a process Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition flag of j equals true and turn equals j. This loop is the only one possible condition where the Pi can be prevented from entering the critical section. And if Pj is not ready to enter the critical section, then flag of j equals false and Pi can enter its critical section. If Pj has set flag of j to true and is also executing in its while statement, then either turn equals I or turn equals j. If turn equals I, then the process Pi will enter the critical section. Otherwise, if turn equals j, then the process Pj will enter the critical section. However, we can see the turn variable indicates which process to enter its critical section. Eventually, once Pj exits its critical section, it will reset flag of j to false, thereby allowing Pi to enter its critical section. If Pj resets flag of j to true, it must also set turn to I. Thus, we can say that since Pi does not change the value of the variable turn while executing the while statement, Pi will enter the critical section after at most one entry by Pi. So we can say the other two properties, that is progress and bounded waiting, are satisfied. Since all the three properties, that is mutual exclusion, the progress requirement and the bounded waiting requirement, are met, we can say the Peterson solution is valid for the critical section problem. Here in the ninth slide, you can see the different phases, which includes different conditions where the values of the variables turn and the array flag differs from each other. And you can find the implementation of code in the slides 10, 11 and 12. And the Peterson solution is the simplest algorithm for critical section problem solution. There are also other solutions like using a simple tool like a log. We say that as the synchronization hardware. We can also use another synchronization tool called a semaphore. The software-based solutions are presented because the hardware-based solutions to the critical section problem are complicated for application programmers to use. Semaphores is also one of the best solutions to the critical section problem. It has a variable types like counting semaphore and binary semaphores and so on. However, Peterson's solution is the simplest algorithm for the critical section problem, and we illustrated a classic software-based solution to the critical section problem known as Peterson solution. Because of the way modern computer architectures perform basic machine language instructions such as load and store, there are no guarantees that Peterson solution will work currently on such architectures. However, we presented the solution because it provides a good algorithmic description of solving the critical section problem, and the solution also illustrates some of the complexities involved in designing software that addresses the requirements of mutual exclusion, the progress requirements, and the bounded waiting requirement. And thank you.